graphing a single line and determining which side of the line contains all of the solutions. So the first equation, or the first inequality rather, y is greater than 1/2 x plus 1. When I plot the line or graph the line, it's exactly, I would graph it exactly as if it were y equal 1/2 x plus 1. So starting with the y-intercept and then using your slope to plot more points. And now it's time to sketch the line, but I have a strict inequality. I have y is greater than. So when I sketch my line, I sketch a dotted line or a slashed line. I don't do a solid line. And now the solution to a linear inequality would be a group of points, and it's the group of points that lie either above the line or below the line. So testing to figure out which side of the line you shade. If 0, 0 clearly lies on one side of the line, it's the easiest point to test. So you come back to your equation and you let both x and y become 0. And then I'll have this, 0 is greater than 1, which is a false statement. So that tells me that all of the solutions to this linear inequality lie in the upper half plane. So I would shade the half of the plane that's above the line. And you can see that the terminology down here. I've shaded the upper half plane, that's the half that contains all of the solutions to this linear inequality, and the boundary would be considered the dashed line. So let's look at the second example. I now have y is less than the same equation, the same line, so let's graph it. And once again, it's a strict less than, a strict inequality. So when I sketch in my line, it's a dashed line. And testing 0, 0 once again. And coming back to my inequality with the substitutions, 0 is less than 1. That is a true statement. So that means that all of the solutions to this linear inequality lie below the line. So I would shade the lower half plane. This is the lower half plane, and the boundary line is the dashed line. Okay, taking this, I now have greater than or equal to, so it's no longer a strict inequality. And if I isolate y, I see that this turns right back into the same line that we've been working with in the other examples. So just to be consistent, we'll keep it that way. All right, so I graph the line. And now, as I sketch the line, since it's greater than or equal to, my boundary line becomes a solid line. So no longer the dashed line, now it's a solid line. And once again, for testing purposes, 0, 0, easy enough to use. Is 0 greater than or equal to 1? And that's a false statement. So that means that all of my solutions lie in the upper half plane. So all of the points on the line, as well as all of the points above the boundary line, are solutions. So when you have the strict inequality, the dashed line, the slotted line, the points along that line would not be considered solutions. But when you have a solid line, the points on the solid line are considered solutions. Okay, looking at the last example, I'm going to isolate y, but I'm going to do it very carefully. If I subtract x and 2, then I have negative 2y is greater than or equal to negative x minus 2. But y needs a coefficient of positive 1, so that means I need to multiply each term by negative 1/2. And when I do that, the inequality symbol reverses. Whenever you multiply or divide a negative number across the inequality symbol, it turns in the other direction. So I now will be graphing y is less than or equal to positive 1/2 x plus 1. So let's plot the line. And this is a solid line because it's less than or equal to. And then for testing purposes, testing the point 0, 0. Is 0 less than or equal to 1? That is a true statement. So that means that all of the points in the lower half plane, as well as the points on the line, are solutions to this linear inequality. And terminology that I'm not overly concerned with, but just to be thorough, the open half plane is just considered the shaded region. And the closed half plane it includes the boundary line as well as the shaded region. But I am not overly concerned with that terminology. And testing points, I'm sure by now you understand that using 0, 0 is always the easiest case for testing, as long as the line does not go through the origin, meaning as long as the point 0, 0 does not lie on the line. When the line does go through the origin and 0, 0 is not a candidate for testing, then you just choose a point that's clearly either above the line or below the line, put it into the inequality, and that determines which side you will shade. And it is possible to have infinite ordered pairs in a solution set. Obviously, when we're shading an entire half of the plane, we have an infinite number of solutions to an inequality.